Okay, today we discussed regarding mechanical design of transmission lines. First we'll discuss sag in overhead lines. While erecting an overhead line, it is very important that conductors are under safe tension. If the conductors are too much stressed between supports in a bid to save conductor material, the stress in the conductor may reach unsafe value, and in certain cases the conductor may break due to excessive tension. In order to permit safe tension in the conductor, they are not fully stressed but are allowed to have a deep or a sag. The difference in level between the points of supports and the lowest point on the conductor is called sag. Following figure shows a conductor suspended between two equal level supports A and B. The conductor is not fully stressed but is allowed to have a dip. The lowest point of the conductor is O and the sag is S. This one is the sag conductor suspended between two supports A and B. The lowest point of the conductor will be O, and this point to this point nothing but your sag. The points may be noted when the conductor is suspended between two supports at the same level. It takes the shape of catenary. However, if the sag is very small compared with the span, then sag span curve is like a parabola. The tension at any point on the conductor acts tangentially. Thus, tension TO at the lowest point O acts horizontally as shown in figure 2. The horizontal component of tension is constant throughout the length of the wire. The tension at supports is approximately equal to the horizontal tension acting at any point on the wire. Thus, if T is the tension at the support B, then the T is equal to TO. The conductor sag and tension. This is an important consideration in the mechanical design of overhead lines. The conductor sag should be kept to a minimum in order to reduce the conductor material required, and to avoid extra pole height for sufficient clearance above the ground level. It is also desirable that tension in the conductor should be low to avoid mechanical failure of the conductor and to permit the use of less strong supports. Calculation of the sag. In an overhead line, the sag should be so adjusted that tension in the conductor is within the safe limit. The tension is governed by the conductor weight, effect of wind, ice loading, and temperature variations. It is standard practice to keep conductor tension less than 50% of its ultimate tensile strength. That is, minimum factor of safety in respect of conductor tension should be 2. We shall now calculate sag and tension of a conductor when I is support at equal level, second support at unequal level. First consider when the supports are at equal level. This is the two supports A and B. The conductor is now hang this portion. This one is point O is the lowest portions. The total length supposed to be L and this the middle portion. So this one is L by 2 and this one is L by 2. And suppose P is a point on the conductor, X by 2 the distance between this, and X is the distance between the middle point O and the point P. And S is nothing but the sag from the middle point O to the reference line of the conductor B. And Y is the point between the sag point and the point P. W0x is the weight of the conductors at a particular distance here, acting downward. It can be proved that lowest point will be at the mid span. When L is equal to length of the span, W is equal to weight per the unit length of the conductor, T is equal to tension in the conductor. Consider a point P on the conductor, taking the lowest point O as the origin. Let the coordinates of point P will be X and Y. Assuming that the curvature is so small that curve length is equal to its original projection, that is OP is equal to X. The two forces acting on the portion OP of the conductor are The first one, the weight of the conductor, weight Wx of the conductor acting at a distance of x by 2 from O. Second, the tension T acting at O, equating the moments of above two forces about point O, we get Ty is equal to Wx into x by 2. That implies y is equal to Wx square by 2t. The maximum dip or sag is represented by the value of y at either of the support A and B. At support A, x is equal to L by 2 and y is equal to S. So sag is equal to W L by 2 rho square divided by 2t is equal to W L square by 8t. Then over second bit, when the supports are at unequal level. In hilly areas, we generally come across the conductor suspended between supports at unequal level. So the figure 3 shows a conductor suspended between two supports A and B which are at different levels. The lowest point on the conductor is O. Let L is equal to span length and H is equal to difference in levels between two supports. X1 is equal to distance of the support at lower level, that is from A to O. X2 is equal to distance of the support at a higher level O to B, that is T is equal to tension of the conductor. The weight of the ice acts vertically downwards, that is in the same direction as the weight of the conductor. The force due to the wind is assumed to act horizontally, that is at right angle to the projected surface of the conductor. Effect of wind and ice loading. The above formulae for the sag are true only in still air and at normal temperature when the conductor is acted by its weight only. However, in actual practice, a conductor may have ice coating and simultaneously subjected to wind pressure. Therefore, the force due to the wind is assumed to act horizontally, that is at right angle to the projected surface of the conductor. Hence, the total force on the conductor is the vector sum of horizontal and vertical forces as shown below. The total weight of the conductor per unit length is the design consideration in the distribution system.